Okay, today let's talk about acceleration. Acceleration is the rate at which I change my position. Okay, so that's all you need to know right there. But first, let's review a little bit. If I have, I want to review position and velocity first, and then we'll extend that to acceleration. Let's suppose I've got a horizontal surface, and I've got a little car that's going to run along that little horizontal surface, little toy car, something like that, and it's moving. And what we did last time was we said, okay, this thing is moving, and so what we can do is represent its position. Describe where it is, but in order to do that I need an origin. So we just arbitrarily pick an origin, like maybe here's 0, and we'll make this 1, 2, 3, 4, 5, 6, 7 meters, and we'll call it the x-axis, and 1, 2, 3, 4, 5, 6, 7, and then what we'll do is we'll represent the object with a dot, because who wants to draw the whole car each time? So I'm going to put a dot right here. And then let's say every second I'm going to look at where the car is. Okay, so maybe after a second it's there, so that we'll call this 0 seconds. And then at 1 second it's here, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7, 8, 9, 10, and so on. Maybe we'll stop when it gets to the end of our number line here. So now I didn't actually draw this diagram before because I didn't really have time, but you can say that, okay, this is 0 seconds at 1, 2, 3, 4. These are times here. And then what I can do then is I can graph, this object is moving at, with constant velocity along this line. And what I can do is I can draw a graph of this. So let's do that. And I can show the position as a function of time. Okay, so here's our position along the x-axis, and this is our time axis. Looks like I went for 12 seconds, so I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I'll just go 2, 4, 6, 8, 10, 12, and this is time in seconds. And then my position, I go from 0 to 7, so 1, 2, 3, 4, 5, 6, 7. So I'll just go 2, 4, 6, so I don't have to write every single one of them. And this will be position measured in meters. So imagine a little toy car moving along at a constant velocity. That is, it's not, it's displacing the same amount for each, period of time, each second. And so, well, at t equals 0, it's right here. And then at 2 seconds, I don't have to plot every single point here. I'm just going to say, okay, at 2 seconds, it was at 2 meters. At 4 seconds, it was at 3 meters. At 6 seconds, at 6 seconds, it was at 4 meters. 6 seconds, 4 meters. And now you're doing this on graph paper, I hope, but I draw these little lines to go up and across just to make it easier to draw. Okay, so at 8 seconds, it's at 5 meters. So here's 5 meters. And notice that this makes 10 seconds, it's at 6 meters. So, and then at 12 seconds, it's at 7 meters. And notice this just makes a beautiful straight line like this. Okay? So remember, when you look at a graph like this, that the object is actually just moving along a straight line. Okay, it's not moving at a diagonal like this, because this right here is a time axis. It's not a spatial axis. It's a time axis. So we're spreading it out. This single dimensional motion along the x-axis, we're just spreading it out over time. Okay. And now, one of the things that we can do is come up with a model for this. Look, this is a this graph that represents the motion of this object, of this little toy car. It is represented by this graph. But notice that it makes a straight line, so we can use the straight line equation to represent the motion of the car. We can develop a mathematical model that describes the motion of this car. I'm going to start off with y equals mx plus b, because that's the straight line equation that everybody's familiar with, right? But remember that in physics, we don't call this the y-axis very often. Sometimes we do, but most of the time it's something else. And in this case, it represents position. And position is represented by x. So I'm going to say x is equal to, now what's the slope here? Well, notice that every second, let's just pick 2 points. Let's make a little slope triangle here. I'm going from 4 to 10 seconds. That's 6 seconds. And I went from, well, it looks like 3, and this is 6. So 6 minus 3 is 3 meters. So it looks like we went 3 meters in 6 seconds. So that's 0.5, right? So 0.5 meters per second. Now what's this? This is my x in my crutch equation. This represents whatever the horizontal axis represents. And so here the horizontal axis is time, t. And this represents the value of y when the value of x is 0. But instead of y, it's our position when time was 0. So when time was 0, our position was 1 meter. Okay? Can you all see that in the back? Am I writing too small? Feel free to come and sit up front, grab a chair and sit up front if you're having trouble seeing. I'll try to zoom in a little bit. Okay? So this right here is a mathematical model that represents the motion of this object through space. Now this object was moving with a constant velocity. Okay? And we represented its and we represented its position as a function of time with this. But I could also draw another graph. And remember, we did this. It's called a kinematic stack. I could say, well, what is happening to the velocity as a function of time? So we'll keep the time axis the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this is time in seconds. Well, the velocity, remember we said that velocity, by definition here, is, well, I'll go ahead and put the limit as delta t goes to 0 of delta x over delta t. That is my displacement over my time. Oops, I'm off screen, sorry. Tell me if I'm off screen, please. All right, so what happens here is you're just taking the slope. But since this is a straight line, you don't need to worry about delta t shrinking to 0 because the slope's the same everywhere. That's what defines a straight line, right? Is a thing with the same slope all the way. So what is that slope? Oh, in this case it's 0.5. So I'll just make 1.0 right here, and I'll make 0.5. This is in meters per second, right? And it's just going to be a horizontal line like this. And so this represents my velocity as a function of time. So if I were to write an equation for this, I would say, hey, the velocity is equal to 0.5 meters per second. Now remember what we did last time is we took the derivative, right? we were taking, we said that velocity is the derivative of position. So look at this equation. If I took the time derivative, if I took dx dt of this, I would just get 0.5 meters per second, right? Because what's the derivative of a constant? 0. What's the derivative of a coefficient times time? The derivative with respect to that time is just that coefficient, and that's the velocity. Does that make sense to everybody? Okay. All right. Well, what if my object did something like this? I mean, this is pretty boring, right? So let's take a look at a situation where, here's my, I'll just draw it qualitatively. Qualitatively means I'm not going to put any numbers on it. So here's my x-axis. Well, I'm not going to. So let's say we start here, and then at time t equals 0, and then 1, 2, 3, 4, 5, 6, 7. So, and I didn't draw this particularly well, but let's say that there's a second between each dot, a second between each position. Obviously, if you took a picture of the car every second and you saw something like this, what's the car doing? It is going faster and faster and faster, right? So it's increasing its velocity. So if I were to draw, and again, I'm just going to do this qualitatively. If I were to draw a position versus time graph, I might get something like this. There's a dot, 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 dot. See, the position here is very much the same, a little farther, a lot farther, okay? And we'll get a curve like this. If you graph the position as a function of time, for this you'll get a curve that looks like that. Make sense? Okay, because each time interval, you're moving farther, you change your position by a greater distance. Okay, well, what's my velocity as a function of time going to look like for this? Just qualitatively. Well, I said that velocity is a function of time is the slope of this guy. So what we have to do is take a look at the slope of this. Well, that looks like the slope is pretty much 0 right there. And then I look at this guy and say, well, look at the slope of that. Remember yesterday we said that, the instantaneous velocity is the slope of the tangent line, right? And so I'm looking at this and I'm going, okay, look at that. It's got more, here the slope is 0, but now I've got more slope. So at this time right here, I'll say my velocity is a little bit bigger. And then over here, look at this time. The slope is steeper, right? So I'm going to make the slope, the velocity is bigger. And then I look right here. Look at that slope. See how the slope is getting steeper? And then I maybe look at this last dot, this last time, and see how the slope is steeper. So what I do is I draw a tangent line on this, and I figure out do a little slope triangle for that tangent line to figure out the delta x over delta t, and that tells me what the instantaneous velocity is, how fast I'm going right at 1, 2, 3, 4 seconds. Okay, and you'll get something like this. And so now what we see is a graph of velocity. When you look at the velocity versus time graph, it now has a slope. In other words, the velocity is changing at a certain rate. And we need to deal with that. See, over here, when my car was just moving with constant velocity, my velocity graph was a horizontal line. And it had no slope. It had a zero slope. But here, my object is moving faster and faster and faster. And so my velocity graph changes with time. So what we're going to do is just what we did last time, is we're going to take a look at the slope of this line. So you just draw a little slope triangle. And this slope triangle will tell you at what rate is my velocity changing. So what's the rise here? The rise is, it's positive. Yeah, that's right. But what am I going to call it? Delta what? Delta V. Right? This is, for this time interval from here to here, this is how much my velocity changed. I was going this fast. I was going this fast, but if I go up and go over this and this, now I'm going this fast. So I've increased my velocity, right? So now what is from here to here? That's delta t. Well, of course, it's delta t, right? And so the slope of this graph tells me the rate at which I'm changing my velocity. We have a name for that. We call it acceleration. Now, acceleration. Now, if you're just going to do a delta V over delta T calculation, like that, this by definition is called average acceleration. Okay? But if you want instantaneous acceleration, if you want to know at what rate am I changing my velocity right now, at an instant in time, what are we going to do to this guy? You're going to take the limit and let delta t shrink to 0 and get a slope of a tangent line. Now, if your velocity is changing at a constant rate like this, the tangent line is the line. Like if I say, okay, at like 1, 2, 3 seconds, what's my velocity? What's my acceleration right here? Well, draw the tangent line. Oh, the tangent line is the line. So you just take the slope of the line. Okay? But you will have situations where the acceleration is changing with time. The rate at which the velocity is changing with time. In other words, this would be some kind of a curve, and you would have to take the slope of the tangent line. If you had an analytical expression for it, you would just take the derivative of it. Okay? So instantaneous acceleration, we use the letter A, is by definition equal to the limit as delta t goes to 0 of the change in velocity over the change in time. Okay? And so, this can be written a little bit differently. We can say that A, the acceleration is equal to, by definition, equal to, well, we could go dv dt. Okay? Now, notice that I put this in parentheses right here. That's because, well, I want you to think of the derivative as a mathematical operator, okay? Do you know what have you heard that term, a mathematical operator, before? Okay, some people look a little confused. So I'm gonna tell you what a mathematical operator is, and it sounds really, scary and official and everything, but it's really very simple. You learned a mathematical operator in kindergarten, or maybe the first grade. We didn't learn it till the first grade, but kindergarten now has become like AP kindergarten or something. But the first thing you did was you took, like, here's 2 dots, and here's 3 dots, right? And so you said, well, how many dots do I have there? Total, I've got 5 dots. And so what you learn to do is say, okay, 1, 2. The first thing you learn in math was how to count. There are 1, 2 dots here. And you learned how to write a numeral that represents 2 of something. And then this is 3. But when you count them all together, when you take this number of dots and you count them along with this number of dots, we have a name for that. It's called addition, right? And so it's a procedure. Now, you've been adding your whole, since you were 5 years old, or even younger, some of you have been adding. And so you don't even think about what it is you're actually doing. But it is a procedure, okay, when you add 2 plus 3. You take 2 dots, you take 3 dots, and then you count them all together. 1, 2, 3, 4, 5. That's a procedure that you follow. Now, what happens is that we make you, and it's a good thing we do, it's very convenient, we make you memorize all these math facts, like, the times tables and the addition facts and subtraction facts and all that. Why? Because you don't want to have to think about it every time you do it. You just want to do it. But what's really happening here is you're following a procedure. 1, 2, 3, 4, 5. Well, we have a symbol that tells you to follow that procedure, that operation. It's called a plus sign. Now, see, a plus sign is a mathematical operator. It tells you what to do with this and this. Okay? Now, there's lots of mathematical operators, that you learn in primary school. You got minus, you got times, you got divide, and then you get into fancier stuff. If you've already had AMA, if you took AMA last year, most of you did, or the year before, you have a dot. Remember a dot? It's a dot product between 2 vectors. Okay. Now, if you haven't had that yet, we're going to do it in here. But in any case, it's an instruction. What do I do with these 2 things? What do I do with this stuff? Well, we now have a new mathematical operator. If you have some function x that's a function of time, this expression right here, we're going to operate the derivative on it with respect to time. So we'll say d dt. Now, it's a weird-looking operator. It's not a plus sign, a minus sign, a times sign, or whatever. But it's this. And then we're going to operate the derivative on this thing right here. Okay? So that's how you think about the derivative. It's an operator. It's a set of instructions on what you do with a particular mathematical expression. Just like 2 plus 3. Okay? This is saying, hey, see these 2 things? Do something with them. And here's what you do. You count them all together. Okay? So, subtraction is something different, and times and divide is something different. Well, the derivative is something different. So I'm going to operate the derivative on this expression. Well, if this x represents position, okay, when you operate the time derivative on a position as a function of time function, you get a velocity function. You get v of t. Okay? Now, if I operate the derivative on velocity as a function of time, oops, I'll put square brackets around it. What do I get? I get acceleration. But this means that acceleration is what I get when I operate the derivative on the position function twice. You see, let's go backwards. The acceleration is the derivative operator operated on the velocity function. But the velocity function is this. So I'm going to say this is this is going to look really funky here. ddt of position as a function of time. Okay? And so, well, this is really awkward to write, isn't it? So what we do is we say, well, the dt, notice the dt is here twice. So we have a shortcut way of writing this. There's two of them, dt squared. And it actually is kind of like multiplying, as you will see. And then how many d's do I have here? I've got two of them, all operated on the position function. So you can think of the acceleration as this. We're operating the derivative on the position as a function of time twice to get acceleration. Okay, so that is, that's what's going on with that. Now, but here's the thing. It's very easy when you're first learning this stuff to get lost in the math and let the math confuse what's really happening. Okay, so what I'm going to do is this. I'm going to draw a position as a function of time graph. And what we're going to do from that is we're going to look just at the slopes, and we're going to get velocity as a function of time. And then I'm going to look at the slopes of that to get acceleration as a function of time. It's called a full kinematic stack. And by the way, you're getting in like 2 days, 3 days, what we do in regular physics over like 3 weeks. And you're doing it with calculus, which they don't do. So we do move quite fast in here, but I hope this is all soaking in pretty well. So here's my position as a function of time. You know what? I can go down here. I don't have to have a positive position all the time. So let's start here. Yeah, let's just do this. Keep it simple. Maybe I'll have it come down a little bit. Well, you know what? I'll make this a straight line. Yeah. Okay. So we move the time over a little bit. So this is time in seconds. Now, here's my position graph. I got to zoom out a little bit because I made it so big. Now what we're going to do, just qualitatively now, just think about what the shape of the graph is going to look like. Here's velocity as a function of time. Now, what you do is you just take like your pencil and you come up with an instantaneous velocity. That looks pretty close to zero, maybe not quite zero, maybe slightly positive. Is that what it looks like to you, right? Slightly positive. So my velocity is going to start off there. And then what happens to my slope as time goes by? It gets steeper and steeper until right about there. Maybe it stops getting steeper right about there. When it stops getting steeper, that's when I do something like this. So I'm going to kind of go like it's getting steeper and steeper and steeper. And it looks like it's a pretty constant rate of increasing the steepness. And then it looks like it doesn't change very much. So it kind of looks like the velocity kind of stays fairly constant for a little while. And then what happens starts happening to the slope. Like right about in here. It looks like the slope starts getting a little bit less and less until right here. What's the slope right here? 0. So right there, the velocity is going to be 0. So something like this. And then looks like it starts really peeling over to the slope gets negative, negative, and then it stays kind of a constant negative. So it looks like it really gets negative fast, and then right about there it kind of stays a constant negative slope, constant negative slope. So it looks like constant negative slope until I guess right about there, and we don't know what's happening after that. Okay, so just by looking at the slope of this guy, I drew this. Does that make sense? Because velocity is the rate at which position changes. Okay, now, and again, this is qualitative, but I bet, I bet it's pretty close. And now, what am I going to do to get the acceleration? Oh, one thing. Notice that what's my initial position? X naught is right here, right? Did it have any effect on where I started my velocity graph? No, none whatsoever. This doesn't care what x is. Velocity doesn't care what your position is. Velocity cares about the rate at which you're changing your position. But your position can be anywhere as far as velocity is concerned. It just wants to know at what rate are you changing that position. Okay, so now we're going to do acceleration as a function of time. Now so I'm going to look at the slope of this. What is the slope doing right in here? It looks pretty constant. And is it constant positive? Yeah, so I'm going to call this a constant positive. And then boom, what's the slope doing here? Looks like and let's extend these lines all the way down. So here it looks like the slope is kind of very quickly went down to 0. And then it looks like right in here, the slope starts becoming negative. And here we have a constant negative slope. And then we have a steep change in the slope. And then right here, it looks like it goes to 0 slope. That is, here the velocity is constant. See how this slope is constant here? That means a constant velocity, which means 0 slope here. Okay? So this is a full kinematic stack where you have position, velocity, and acceleration. Now this is qualitative, but what I'm trying to do here is show you that velocity describes the slope of position, acceleration describes the slope of velocity. Slope, what does that mean? That slope is the rate of change of position. That's velocity. Acceleration is the rate of change of velocity. Okay? So it takes a while to get used to thinking like this. One of the biggest mistakes that students make when they're thinking about this and trying to solve problems and understand what's happening, students quite often confuse velocity and acceleration. And so if you think about it graphically and about what a derivative means and so on, you might be able to think your way through those misconceptions. And we're going to work a lot of problems where we're going to work through those misconceptions. So just to summarize, we've got a new term here, acceleration. Acceleration is the rate at which velocity changes. So it's the derivative of velocity. And one of the things we can do, by the way, one last thing. I was drawing the dots here. This is called a motion diagram. And if I have an object that's doing this, maybe it starts off here, and then it goes a little bit, and a little farther, and a little farther. And these are equal time intervals. This represents, the dot represents, this is my position axis here. When I draw time, shoot, that's exactly what I didn't want to do. This is my position in meters or centimeters or something. And this is my origin. And then you can put the time 0, 1, 2, 3, 4, 5, 6. And notice this little diagram represents position as a function of time. Except it's not really a function. It's just, it shows, okay, here's my positions, and here's where I am in time, and I'm representing the dots, or represent where it is. Now I can represent velocity by drawing a little dot here. Or I'm sorry, little arrows. Okay? And so these arrows represent velocity. And then above or below, it doesn't really matter, I can put a little acceleration arrow. And what does this acceleration arrow represent? It says, hey, next time I'm going to draw the arrow this much longer. That is, I'm going to increase my velocity by this much each time interval. So this is called a motion diagram right here, and they're kind of helpful sometimes in trying to figure out what the difference between acceleration and velocity and position. So anyway, any final questions? I think we're okay. All right. That is all.